Hey everyone, ever wonder how AI learns to focus on the most important features of data? Like how a self-driving car spots a pedestrian, but ignores the passing trees. Today, we're diving into a fascinating problem in neural networks, adaptive sparsity, and why some models struggle to do it right. Let's break it down. Imagine you're trying to teach a machine to recognize a cat in a photo. Instead of memorizing every pixel, the AI needs to focus on the key details, the ears, the eyes, the whiskers. That's where sparse autoencoders come in. These are neural networks that compress data into a compact code, like a secret shorthand. But here's the twist. They force the model to use only a few active neurons at a time, like a spotlight shining on the most critical features. This makes them super efficient and easier to understand. But there's a catch. Traditional sparse autoencoders use penalties, like L1 or L0 norms, to enforce this sparsity. Think of it like a diet, you're supposed to eat less. But here's the loophole. If you shrink the plate, scale down the network's weights, those penalties become meaningless. It's like dieting by switching to a smaller bowl, no real change in behavior. This means the model can fake sparsity without actually learning the right features. Now let's talk about variational autoencoders, VAEs. These models add a dash of randomness to the mix, letting the AI explore multiple possibilities instead of rigidly picking one. This helps avoid local minima, those pesky traps where the model gets stuck in a suboptimal solution. But VAEs have their own issue. They often enforce fixed sparsity. Imagine a camera that always uses the same number of pixels to snap every photo, whether it's a simple logo or a bustling cityscape. It's inefficient because it can't adapt to the complexity of the scene. Enter VAEase, a clever hybrid model that solves this problem. Instead of relying on fixed rules, it lets the model learn when to be sparse and when to be dense. Think of it like a flexible spotlight that adjusts its beam depending on the scene. Here's the magic. VAEase uses stochastic optimization to dynamically decide which features to prioritize. It's not hard-coding rules, it's letting the data guide the process. How does this work? Traditional sparse autoencoders use L1, L0 penalties to zero out inactive neurons, but these can be gamed by scaling weights. VAEs avoid this with L2 regularization, which limits weight growth. But VAEs lack the adaptive sparsity needed for complex tasks. VAEase bridges this gap by combining the best of both worlds. It introduces a probabilistic sparsity constraint that evolves during training, ensuring the model only activates neurons when necessary. Mathematically, this avoids the weight scaling loophole while maintaining interpretability. Why does this matter? If models can learn to focus on what's truly important, they become faster, more efficient, and easier to interpret. This could revolutionize everything from image compression to medical diagnostics, where clarity matters. And the best part? The math shows this isn't just a clever trick, it's a fundamentally better way to let AI see the world. So the next time you interact with AI, remember, behind the scenes, models like VAEs are working hard to make sense of complexity. By mastering adaptive sparsity, we're not just building smarter systems, we're building ones that understand what they're seeing. Thanks for watching and stay curious.